Hello and welcome to the ArcGIS Pro SDK for .NET session called An Overview of the Geodatabase API. My name is Rich and I'll be here with my friends Alex and Ling to walk through a number of different topics. We're going to start with talking about some of the architectural principles behind the Geodatabase API, then kind of go into an overview of all the different areas that are involved. We'll talk about what's new and some best practices, and then we'll wrap up talking about the road ahead and learning more. So what we're not going to cover is the Pro add-in model. There are other sessions for that. Likewise, with editing, there are a number of sessions there. And we're also not going to be doing a detailed comparison between ArcObjects and the Pro SDK. So with no further ado, I'm going to hand things over to Alex to talk a little bit about architectural principles.
Thank you, Rich. So now I'm going to go over the architecture of the SDK. So of core.data. Basically, this is how the SDK is set up. You have your managed side and your native side. Managed consists of C# code, all the API calls, and the native consists of the C++ code, which will in turn eventually call down to ArcObjects. ArcObjects will be used for your main purposes. So let's say you're building a desktop add-in, you're going to use ArcObjects to set everything up. If you're building a standalone app through a core host, ArcObjects, we have like functionality down there for you to do that with. So the client is going to make calls into C# code, the API calls we give you. These calls turn down to ArcObjects and then do basically whatever you called. So essentially, some of the C# API calls involve core objects like the geodatabase, feature class, table. Some API calls for a geodatabase include, for example, open dataset. For table includes get ID. So these are some examples users can call for the SDK. So for API characteristics, we try to make it as minimal as possible. Minimal as in we contain everything within a couple of namespaces. The main namespace for geodatabase is arcgis.core.data. This is where the geodatabase core object I was referring to earlier comes into play. It comes into this namespace. So if you're using geodatabase feature classes, tables, cursors, they're all inside core.data. There's also smaller namespaces that are more specifically tailored. So example, ArcGIS core.data.raster. There's a core.data.utility network, .mapping. These are more tailored to whatever users, if users want to be more specific in whatever they're trying to do. So you can use those namespaces as well in addition to core.data. Another key characteristic is all of core objects is strongly typed. So for example, you have your feature classes in your table. They all come into a data set. But a feature class is inherently different from a table. If you're calling, let's say, a table has a getID method, a feature class doesn't. But let's say if your data set is a feature class and you try to call getID, it'll basically throw an error saying it doesn't exist on this specific object. This is just to make it easier for users to debug. Since there's no implicit casting going on, everything's explicit casting, so everything's working as the developer intended. Makes it a little bit easier to navigate. Another good characteristic about our API is better exception handling. Originally, if you're just using ArcObjects, errors from HResults, for example, would give you this cryptic number, kind of hard to decipher. What the SDK gives is a translate exception, such as cannot acquire a lock, for example. It's a lot more specific and a lot more easy to read versus a number like that. So it will help you understand what the potential problem could be due to or what the potential problem is. So that's another thing we offer. Another thing about core objects is data manipulation language only, DML, meaning you can't create schemas such as creating feature classes, creating tables, creating geodatabases, creating domains, adding fields, whatnot. Main things you can do is insert rows that you're allowed to do inside tables. If you want to do schema operation like create a feature class or create a geodatabase, you would have to use the GP tools, geoprocessing. In order to do that, you just need to use the geoprocessing namespace. Basically, what you do is instantiate a geoprocessing object and then just call execute tool async. This is used to call whatever GP tool that you need. So if you see data management tools, they're all appended with the underscore management. It's like create feature class underscore management. That's one way to decipher what kind of tool you're using. So yeah, if you want any schema creation operations, you have to go to GP tools for now. Another thing that's important with the SDK is the threading model. How it works is essentially core objects and arc objects, they have thread affinity to main sim, meaning that all method calls will have to be on this thread. It can't be on a worker thread. If you did call some of our core objects methods on the wrong thread, you get the call on wrong thread exception. One way to fix this, you can use task.run. Task.run will make sure it'll make sure your method call is called on the correct thread. The only problem with task.run is that if you have multiple tasks running at the same time, they could finish at different times. So let's say you have task 1 is trying to finish, task 2 starts up later on but finishes faster. This could lead to a lot of corruption within the data or crashes, even crashes at that. You don't really want that, so we introduced queuetask.run. Queuetask.run will make sure all of your tasks are called in the correct order for concurrency reasons. This way you don't have to worry about tasks running out of order, and you don't have to worry about methods being called on the wrong thread. Everything will be called on the correct thread in the correct order with queuetask.run. You can also read Working with Multi-Threading ArcGIS Pro, our doc. We'll have more information on that. But that's the main gist of the whole threading model. Now, back to Rich for an overview of the GeoDatabase API.
Thanks, Alex. Let's move now into giving an overview of the GeoDatabase API. Now this is a pretty extensive API, so in the hopes of keeping it a little more manageable, I broke it up into 6 sections: data stores and data sets, queries, versioning, core host, plugin data sources, and attribute rules. Let's tackle these in turn. First, let's start with data stores and data sets. So before we go into details, I want to kind of outline the general GeoDatabase access pattern. So generally speaking, when you're working with the GeoDatabase API, you start with a connector. That's the thing on the left-hand side of this diagram. So a connector class is used to open a connection to a data store. Now a data store holds a bunch of data sets, and you use that data store to open a data set. That can be a table or a feature class. So tables and feature classes, against those you execute queries to create row cursors. And then you iterate through that row cursor to fetch individual rows or features. So that's a pattern. We're going to see that on a few other places today. So let's start with connectors. There's a set of connector classes that are used to define a connection, basically. So we have a file system connection path, which is used to open up a shapefile. SQLite connection path, file geodatabase connection path, service connection properties to connect to a feature service, and so on. Of course, the big one is database connection properties to connect to an enterprise geodatabase. So a data store is a container of spatial and non-spatial data sets. As we've mentioned, you create it from a connector. Now from a data set, you can also get its data store by calling dataset.getDataStore. Now the most common set of dataset, well, most common to me anyway, is a geodatabase class. So a geodatabase class is used with enterprise geodatabases such as Oracle, SQL Server, Postgres, or HANA, file geodatabases, as well as feature service geodatabases. Some other kinds of data stores supported, though, are file system data stores, which work with shapefiles, and an actual database class. Now, a database class represents a connection to a database management system that does not have geodatabase enabled. So there's none of the GDB system tables, and ArcGIS doesn't have any other data stored in that database. It's just plain files. So as we mentioned, data stores can be used to open data sets, and the simplest and the most basic data set is a table. Table contains 0 or more rows, and it supports search and select, and we'll talk about that in the query section. So some ways to open a data set, to open a table rather, is to call the open data set method on a geodatabase, passing in a table name. You can also get it from a feature layer, and you can also get it from a row. Now a feature class, the feature class inherits from the table, and it represents a table that has a shape. That shape can be a point, line, or polygon. It contains 0 or more features, and it supports spatial queries and selections. And much like with tables, you can create them 3 different ways. You can open a data set from the geodatabase, you can get a table from the feature layer, you can get a table also from the row. So one of the things I show there is geodatabase.openDataset with feature class in the angle brackets. You can also open a feature class as if it's a table, just using that last line of code there at the bottom. Another kind of dataset that we support is a feature dataset. A feature dataset is a collection of related datasets with a common coordinate system. This is often used to organize feature classes for things like topology, network datasets, utility networks, terrain datasets. It's kind of a container of additional feature classes. Another kind of dataset supported by the system is a relationship class. This is a geodatabase stored relationship between tables and feature classes. So this is typically made up of an origin and a destination table, and as part of that relationship class, we also define the cardinality of that relationship. So there's 2 kinds of relationship classes. There's a standard relationship class, which may or may not have a backing table, and an attributed relationship class. Now, an attributed relationship class does have a backing table. What that means is there's a separate table in the geodatabase that maps the rows from your origin table to your destination table. Now, attributed relationship classes, which you typically see when you have many-to-many relationships, you can also add user-defined attributes to those as well. Now, once you get a data set, one way we have to get information about it is a class called a definition. Now, a definition is used to describe the schema and any unique properties of that data set. So for example, you can get the fields of the data set. You can find out if a data set has a global ID. Now, we separated this from the data set itself basically to facilitate a lightweight way of getting to this data. So opening a data set itself is comparatively expensive, but you can get the definition without opening the data set itself. So you can see at the bottom there it says geodatabase.getDefinition. You can get the definition of a particular table, or you can get the definition for all the tables in your geodatabase. So what that will do is it allows you to get that list of definitions, perhaps present a list of names to the user, and then open the one that you care about. All right, so you have your data sets, you have your information about that data set via the definition. Let's talk now about all the different ways you can query your data. Now we'll start with simple search, and then I'm going to describe some of the other methods we have, including query defs, query tables, joins, and query layers. All right, let's start with the easy one. I would say, depending on your application, certainly most applications, 95% of the time you're going to be doing a simple basic querying using a search or a select. Now the search is the most basic one. You call table.search. You pass in a query filter, which we'll talk about in a minute, and you get back a row cursor that lets you go through those rows. You can also do table.select, which will return a selection set. That's a lightweight way if all you want to do is highlight the features on the map. So what are these query filters? A query filter is used to restrict what records get retrieved from the table. So typically the most important thing is the where clause. You can pass in the where clause, which of course gets translated into SQL or its equivalent. You can also specify a set of subfields, and what subfields will do is allow you to get back only those fields that you need, so it could reduce the amount of data that you're moving over the wire. You can also use the pre- and postfix clauses to do things like distinct and order by on the SQL. Now there's a plain old query filter, but there's also a thing called a spatial query filter, and that is a subclass of a query filter, and that just allows you to restrict the records retrieved by using a spatial query. So you can say find all the features within a given envelope. Now in either event, when you call that search method with your query filter or spatial query filter, you get back a row cursor. Now this represents a database cursor and allows you to walk through a collection of rows. So move next will position the cursor to the next row in the sequence. Returns false when it's finished, and then current returns the current row. Now, and if later on in this presentation, Alex is going to walk through the whole pattern for how you typically use this, and so I won't steal his thunder. In addition to searching, I said search is what you're going to use 90% of the time, but there are many other cases where you need additional kinds of queries. So the first of these that are supported by ArcGIS is called a query def. Now, query defs work with file geodatabases and enterprise geodatabases. It takes a set of tables. You can do a query def on a single table, or you can join two or more tables within the same data store. Now, this is creating kind of a virtual table, so you can't, if you call get table on the rows you get back from this, you're not going to get anything of value. It does allow you to do a join involving shape or returning the shape. The shape is returned on the leftmost table in the query def. And the result is read-only. So the way that works is you call the geodatabase.evaluate method and pass in a query def. So here's an example of a query def. First we start by defining some strings, then we create the query def object itself. And you can see for the tables clause, we are creating a string, which is basically the inner join between the parcels table and the owners table using the specified primary and foreign keys, and adding in a postfix to order by a particular owner name. Now another kind of query we support is a thing called a query table. Now a query table creates a virtual table. And the reason why you'd want that virtual table is if you want to create a map layer from it, or if you wanted to pass this as input into geoprocessing. So this kind of works by creating a query table description, which is a name and a query def and a set of fields, and then you call open query table on the geodatabase to get back your query table. We also have a thing called a join. Now a join is used to combine fields from two tables, resulting in a single table representation at the end. Now what's interesting about this is it supports tables from one or two different data stores. So this is the only way you can join tables from two different databases. Now you create it using a relationship class. If it's a single table, you can use a relationship class stored in the geodatabase, or you can create a virtual relationship class. Now the result of your join is read-only, however, it will reflect updates to underlying tables. So I mentioned if you're doing a join between tables in different data stores, you're going to need to create a virtual relationship class. So let me kind of lay out the pseudocode for how you go about doing this. First, you create a virtual relationship class description. Then you take, on the leftmost table, you call table.relate_to, and you pass in the right table and that virtual relationship class description. And what that will do is it will create a virtual relationship class. Then you pass that resulting virtual relationship class to the join description constructor, and then you pass that to the join method, to the join constructor, and that's how you go about creating a join. So from a join, you can get the join table. However, there's no definition on that join table when that table is from multiple data stores. So whenever possible, if it's using a single data store, of course, we'll try to push that join to the database and have the database do that join on its end rather than fetching all the rows and doing it on the client side. One more thing worth pointing out is a database and a query layer. Now, if you remember from a few slides ago, I talked about databases, and a database is a data store without the geodatabase tables in it. So these can be queried using a construct called a query layer. So to do this, you create a query layer using the database getQueryDescription method. You can get this from a table name, or from a string that is a full SQL query. So you can modify the query description, and then you pass that query description to database.openTable, and that will get you back a table. So lots of different techniques to go through and execute queries. And if your head is spinning at this point, you're not the only one. And I certainly encountered that when I first started dealing with this. So what I have done, and this is a great slide to keep as a reference, is this is a little flowchart telling you which kind of query construct you should be using. So starting from the upper left, if you have a geodatabase, if it is not a geodatabase, then you immediately have to go and use a query layer. If it is a geodatabase, if you want just one geodatabase, you move here. If it's many, you're kind of forced to use a join. For one geodatabase, then you have to ask yourself, do you want to take the result of this query and use it as a layer or an input to geoprocessing? If you do, you want a query table. Otherwise, you go down here to the center right, and it says how many tables, one or many. If it's just querying one table, just use the basic query using the search. That's your simplest option overall. If you have many tables, you ask yourself this question here on the bottom right, one-time query. If you're going to do it many times, you want to create a query table from that. Otherwise, come over here and ask yourself how good you are at SQL. A join is simpler. If you don't know SQL, that's probably the good bet. Otherwise, you can go ahead and use a query def. So hopefully you'll find this table useful. So a couple additional caveats. With feature service databases, there's some additional restrictions. They don't work with joins and they don't work with query def. That's because at the end of the day, you're not executing a SQL statement. You're fetching rows using a REST API. Again, joins are simpler. Query defs have more capabilities. Okay, let's go roll this back a little bit and talk about some simpler kinds of queries that you can do. A very simple one is just sorting a table itself. So you can create a row cursor where everything is sorted. That's created with the table sort description. And the table sort description has a query filter and a set of sort descriptions, so you can sort by multiple fields. Each field you can determine its sort order, and its case sensitivity. So you can sort by state name ascending, state capital descending, or something like that. Another way you can query data is to actually just calculate statistics on that data. So we have a number of routines that allow you to calculate statistics on table fields. So for example, you could do counts, sums, min, max, average, and standard deviation. We include support for group by and order by, so you can get the average population of cities grouped by state and ordered by that number. These calculations will be computed on the server if supported. A couple differences: if you're used to using calculate statistics in Pro, it's worth pointing out that in Pro, the Pro user experience and the geoprocessing work on the layer level, whereas the table.calculate statistics works on the table or feature class level. Okay, so I've been talking a lot, and we haven't looked at a whole lot of code. So I'm going to turn things over to Ling, and Ling is going to walk through a demo on data stores and data sets, and then she's going to walk through a demo on calculating statistics.
Thank you, Rich. I'll give a quick demo on a simple add-in to walk through how to open data store and get dataset definition for selected data paths. The data store type here, a type of connect containers which is equivalent to workspace in the ArcObjects API, such as the file GDB, enterprise, feature service, SQLite, and shape files. Let's take an enterprise workspace, geodatabase, browse to my SQL Server, enterprise geodatabase here. Once we do load the data, it will populate the data types and then list the dataset based on what type of the data you selected. How could we accomplish how could we accomplish this if we work with ArcObjects? We need to open the workspace. We need to then open the dataset to get such information like the fields, index, feature class name, object ID name, and all properties like this. But with Pro SDK, we could take advantage of the lightweight mechanism of get definition to retrieve dataset metadata without the expensive cost of opening the dataset. Now let's take a look at the code. Click Load Data. The load data will evaluate the data store type, opening the data store and the populated dataset type accordingly. The connector here varies with the data store type. To open the file geodatabase, an instance of file geodatabase connection path should be passed into geodatabase connector. For enterprise geodatabase, it's a database connection file. And for feature service, it's service connection properties. For shapefile, there's it can be opened using the file system connection path, and with the type specifies the shapefile. So let's check the feature class. Once we open the data store, we could get definitions for the dataset. The way get definition work varies depending on the data store type. If it's a geodatabase, like here, we can get definition directly based on the dataset type. Either it's a table or feature class or feature dataset, relationship class, attributed relationship class. But if it's a database, we do not, which means it do not have the geodatabase schema, we cannot get definition directly. What we do is we get table names and get query description for each table. Then we get the definition just for the table, for the tables. For shapefile, since not all files in the shapefile directory could get definition, the only data type that is supported by shapefile via the file system data store are the tables and the shape feature class. So what I do, we will need to get the file first, the shape file or the DBF file, and then get the definition for the files. So the get definition methods exist for all data store, just in different ways. Data store definition is an abstraction that is conceptually equivalent to data element in the Objects API. One more thing I want to mention about the get definitions is it's one of the few objects that in the core.data API that is thread agnostic, which means you don't have to wrap it inside the qtask.run. It can be run in the UI thread. Once we get the definition, we can see you can see all the detailed information populated in this box. You can also find the subtype with the code and the description here. So that's it for the data store demo. GeoDatabase provides powerful tools to calculate statistics on table fields. These statistics are computed on the server if supported. Statistics are calculated by calling the calculate statistics method on the table or feature class. In this add-in, let me browse to my add-in here. Yes, the calculate statistics. In this add-in, we'll have to switch to this map. And this is my selected table or feature class. We need to set the selected field, the statistics function. The field will populate here, and let's see major defense offense type. The statistics function, let's do the count, and the group by field. Let's check what's behind the code. Our group by neighborhood, let's see, calculate statistics. I don't have a map selection yet, so here is how the statistics are calculated. The calculate statistics takes a table statistics description object to specify how the statistics should be done. The optional order by and the group by field property will group the rows together, and the order by property will sort those groups. But if the underlying data sort does not support group by or order by, for example, the shapefile, these properties will be ignored. The return value is here. The return value is the table statistics result. If no group by was specified, or if the underlying data store does not support group by, only one table statistics result is returned. Otherwise, there will be one instance of table statistics result returned for each field grouping. The group by property in the result on the statistics result describe the grouping that was returned. It's a key value pair represents the field and the value of the field for the group. One key value pair will be returned for each field in the original group by. In the statistics result object, Since even though we have all the count, sum, mean, max, average, all these functions, only our property are filled in. Like if I only select, we do the statistics for the count, so this count property will be filled in. Back to the add-in, we'll see, let's check the result. So I have the statistics done on different different neighborhood with a count for major offense type. This is done for the whole feature class. If I have a small area that I want to do the statistics for only this area, I do the selection first, and then let's see what's going behind. Now we have map selection. The map selection, it's a call.data selection type. We can do search on the map selection. The result of the search is a raw cursor. Which is a normal enumerator. Raw cursor move next, and the cursor move next return to the Boolean representing whether the end of the record is reached. The raw cursor current returns the current feature or row. We can loop through the cursor to get the selected feature until you got to the end of the selection. The envelope here, we use the envelope builder to get the extent of the selected features, and then do the special selection with that envelope. Now let's see what the result we get with only the small area. That's the area I get, that's a neighborhood for this area I selected. That's it. That's it for the statistics demo. Now back to Rich. Thank you.
Okay, thanks, Ling. Got a few more topics to cover in our overview here. Let's kick it off with versioning. So versioning support is based upon a version manager class. The way to get to this is, first of all, you call the geodatabase is versioning supported method, and this will return true or false. If it returns true, then you can say get version manager and get back this version manager. Now, this particular class allows you to create versions, connect to a specific version, list all the versions in a geodatabase, get their properties. One other thing you can do, which may not be immediately obvious, is that you can get differences between tables and feature classes from different versions. The way this works is you connect to a version and then open the table from that version, then call table.differences on it. Now, the version object itself has a number of properties. You can alter or delete the version, you can refresh it, and probably most importantly, reconcile and post. Now, the interesting thing, if you look at the methods on the version class, is there's no post method. And the reason why that is because you want to post immediately after doing a reconcile. So what you typically would do is you call reconcile, you pass in this reconcile description, and then you set the with post property on the reconcile description to true. And that's how you get the reconcile with the post. Let's talk a few minutes about Core Host. Not everyone is aware of Core Host, but what Core Host does is it allows you to create a standalone application or a headless application without the Pro user experience. This is sometimes useful if you're writing like a data translation program or something of that kind. One, you are restricted. You are restricted to using basically the geodatabase, the core host routines themselves, and geometry. So, for example, you can't call geoprocessing from a CoreHost application. But what you do if you need to run a GP tool is you shell out to Python and call it directly from that way. So to create a CoreHost app, you reference arcgis.core and arcgis.corehost in your application. You set it to be a 64-bit app with the STA thread attribute. The first geodatabase call you make, or rather the call you make before any geodatabase calls, is host.initialize. And what this will do is it will use the Pro license on that machine to check out the license and so forth. So that's the routine you use when you start things up. Now you don't have access to the editor. Instead, when you're editing, you use the geodatabase.applyEdits call. So that applyEdits takes a delegate, which allows you to stuff in all of your edit calls, and it defines the scope of a transaction. Let's talk a minute about plug-in data sources. So, ArcGIS Pro can display and analyze data from many different formats, and we've covered a lot of those today in the connector and the data store talk. But there's many other data formats that we don't support. For example, there could be other databases such as MySQL, or maybe you have a proprietary file-based database or data system, or just simply a file you want to expose in Pro as a table or a feature class. What the plugin data source framework allows you to do, it allows you to make these data formats accessible inside ArcGIS Pro. You can execute queries, you can perform analysis, and display features on a map. We don't provide editing. This is read-only access only. But you would be able to edit it. You would just use, whatever proprietary editing APIs exist for those formats. So the way it works is we have a new connector object in the system called a plugin data source connection path. And the framework itself provides 3 template classes. And what you as a developer do is you define a concrete derived class from each of those templates. So you would create a concrete subclass from plugin data source template, from plugin table template, and plugin cursor template. And you provide these 3 things, and then you use the plugin data source connection path to connect to your data and display it as a table or feature class in Pro. Let's talk about one more thing, attribute rules. So attribute rules are a fairly new piece of the system that allow you to enhance the editing experience and improve data integrity. What it does is it allows users to write rules using the Arcade scripting language. Now, these rules are assigned to feature classes and subtypes using geoprocessing tools. So a couple different kinds of attribute rules. We have constraint rules. Now, constraint rules execute automatically at edit time, and what they do is they restrict invalid edits. So you could write a rule that will prevent data from being entered that fails your rule. You can create a calculation rule, and a calculation rule will populate an attribute based on the value of other attributes or other features. Now there's 2 ways to write these. You can write a immediate calculation rule that happens automatically at edit, or you can write a batch calculation rule. And finally, we have validation rules. So validation rules also run in batch, and they perform quality assurance checks on existing features. And if they fail to check, if the feature fails to check, it'll create an error feature associated with that original feature. So I guess the first thing to mention is these immediate rules, the immediate calculation and the constraint rules, they fire automatically when edits take place. They're supported on all enterprise geodatabases as well as file geodatabases. There's no SDK support. They just work. You make an edit, that rule will fire. The second kind are the batch rules. These are batch calculation rules and batch validation rules. So these rules fire explicitly when you call the evaluation process. So currently they're supported on feature service workspaces using branch versioning, using ArcGIS Enterprise 10.7, and this evaluation process can be called from the SDK. So the way this works is from the geodatabase, you get an attribute rule manager. And following the same pattern we talked about for versioning, you start by calling is attribute manager supported, and if that returns true, you call get attribute rule manager to get it. Now, if the attribute rules support validation, you want to check first the is validation supported, and then you can call evaluate. So there are some additional SDK capabilities. You can fetch the error features that come back. You can mark errors as exceptions to indicate that this feature isn't really an error. You can also fetch the original features that generated the errors. Let's wrap up by talking about what's new in ArcGIS Pro 2.4 and 2.5. These are the two releases that have occurred since the last time we talked at the Dev Summit in 2019. First of all, we've added much better support for historical versions. So an historical version is a read-only representation of your geodatabase at a specific time. So this only works with archived data sets. So if it's versioned or if it's non-versioned archiving, this will work. You can create what's called an historical marker using a routine called create historical version. And basically how this works is you pass in a name and a timestamp. So you can create an historical marker called the Twin Pines Mall Safety Incident and pass in the time of 1:15 a.m. on October 26, 1985. Google it. You can also connect to any particular time or a historical marker by calling the get historical version routine. So, a couple other things, kind of the geodatabase grab bag, if you will, some other changes that we've made in 2.4. We provide some extension methods to evaluate attribute rules and to update errors inside an edit operation. So if you're running inside Pro, you want to prefer these routines, evaluate an edit operation and update errors in edit operation rather than the low-level ones. What these routines will do is it will create an edit operation and then it will run evaluate or update errors, and then it will refresh the map properly. So, of course, the main thing of putting in an edit operation is now you can undo and redo it. So that's definitely what you want to do inside of Pro. Added a new constructor for version description, makes it a little bit easier to use. So in the past you had to create the class and then set 3 properties on it. Let's see, we provide access to the featured data set from a feature class or relationship class. So get featured data set. In the past you'd have to go to the database itself, get the featured data sets, and then iterate through the featured data sets to find out the feature classes, and that would be the only way to determine the feature data set from a feature class. So it provides a much easier back pointer. And we shipped plugin data sources at 2.3. We just made some changes and improvements in 2.4. All right, so I'm going to now turn things over to Alex to talk about some best practices when using the geodatabase APIs.
Okay, thank you again, Rich. So now I'm going to go over best practices. The main practice that we're going to go over is garbage collection. So just remember to dispose all of your core objects. So as you know, there's a garbage collection that runs. It'll be exposed of no matter what. The only problem with this is that if there's a connection being held or a lock being held by any of the core objects like geodatabase or feature class, you don't know when they're going to be released for a garbage collection. They will be released, but you don't know when. So if you're worrying about memory management or anything like that, you would want to have these released when you want it to be released, more deterministically. In order to have a more deterministic control over these objects, we would want to call dispose when we're done using them. Dispose will basically do the same thing as a garbage collection or release it for you. So alright, before I go into that, these are some of the objects that you should dispose of because they're holding connections, like geodatabase, feature class, row cursor, version manager, Make sure to dispose of these when you're done using them. So there's two ways to dispose of objects. The first way is a try finally block. So for a try finally block, if you look at this little code snippet, you see at the top there's geodatabase equals null. We're just initializing all of our core objects. So these are some things we will want to dispose later on if we initialize them, right? So since we're initializing them here, we will create a try block. We will initialize all our core objects inside this block and do whatever calls we need with them. Once we're done, the code will enter this finally block. It will check every single object, or it should check every single object depending on how you write it, but make sure you check every single object. If they're non-null, explicitly call dispose on them. That way everything they're holding is freed, so your program will be working as intended. This try finally block works because even if there's an exception, let's say inside your try, you call some method illegally and your program crashes, for example. If even it does that, this finally code will execute and it'll dispose of your objects for you. So this is one way that works. So yeah, again, try finally, create your objects outside, do whatever you want inside your try block, including initializing your core objects, and you're finally dispose of everything that's not null, basically. The second way is a little bit cleaner. It's going to be using the using statement. How using works is you have your using right here, then you have an initialization of a object. This is where you want to put your core object like geodatabase or feature class or row cursor or version manager, for example. How it works is once you leave this using block at the end of the brackets, dispose will be called automatically for you on this core object right here. So again, kind of similar to try finally, instead of initializing the geodatabase right there, we'll initialize inside the using. And after the using is done, it's guaranteed to be disposed of. So this is a lot cleaner. We don't need to write extra try finally blocks. We only need one main block for it. I would prefer it this way. This way is just a lot more simple than a try finally block. So another thing you have to note of, some of the API calls will actually kind of create a new core object. For example, row cursor. Row cursor has an internal member called current, storing the current row. If you're calling move next, it's basically going to move that current row to a new row, making another row object, which should be disposed of. If you look at this little code snippet, from face value, it looks fine, but the only problem is, again, the row cursor's current member is not being disposed of, even though we're moving on to the next row. We're creating a new row. So the way to dispose of this properly is before you call move next, which is a Boolean method, make sure to dispose of the current row that you're on, or the row cursor's on. This will make sure everything's disposed of properly and your objects are used properly, basically. You could also use using statements. It could look a little messy depending on how you use it, but this way you don't have to worry about like try finallys or anything. But it looks pretty simple, I hope. One more thing you need to worry about is to not create static variables. The problem with static variables for core objects is when you load an add-in, these static variables are executed not on main sim, but on the GUI thread, graphical user interface thread, which is, again, not the correct thread due to thread affinity. Therefore, your core object's gonna be called in the wrong thread. It will throw a constructor on the wrong thread exception. Therefore, the basic idea is just do not use static variables for your core objects. And that should be it for best practices. I'm going to turn it back to Rich for the road ahead.
Let's end by just talking a little bit about the road ahead and then talking about some resources for learning more. So in the near term, in the next release or so, we've got a number of small enhancements planned to the versioning API. We'll allow you to explicitly ask for which versioning type the database supports, whether that's a branch or traditional versioning. We'll allow you to get a list of version names rather than getting a list of versions. So what this does is just a much faster way of if you want the user to pick from a list, for example, of versions, you can just say get version names and get a list of strings and then open the version using that string as opposed to getting all the versions, which can be a fairly time-consuming thing, relatively. We're planning on exposing reconcile conflict detection type and conflict resolution type. We're also planning to allow you to change the owner of a version. A little small enhancement is allowing support for getPath method on the data set. So what getPath lets you do is it allows you to get the fully qualified name of a data set that you can pass to geoprocessing. So it makes it a little bit easier to call into the geoprocessing API using the Pro SDK. Another thing we're looking at is feature cursor support. The idea here is we'll allow you to do fast inserts in a core host application. So this is using some low-level cursor routines that allows you to, in many cases, create data much faster than you can when you're individually creating rows one at a time. Longer term, some bigger projects that we're looking at and getting started on now, we are planning on adding some DDL capabilities to the Pro SDK, allowing you to create tables and change fields and things like that. So that will probably roll out over a set of releases. In addition, topology API, we know that that is a hole in our system that we're working to fill. All right, let's end just by talking a little bit about how to learn more. I'm sure you got a lot of information today, but there's a lot more available online. If you go to the ArcGIS Pro SDK homepage, which you can find either with the link above, or you can just search for the ArcGIS Pro SDK using your favorite search engine. If you click on this little geodatabase thing down here, you can read a pretty big document that goes into much greater detail about how the geodatabase works, all the different classes, and so forth. Definitely recommend doing a read through there. We also have a link to a set of samples. We have a large set of samples for the geodatabase. These are standalone add-ins, standalone programs. You are allowed to write your own. This is a GitHub site. It's a community site. We welcome submissions from other non-Esri folks. And also, if you have suggestions of things you want to see here, please let us know. Also, going back to the Pro Concepts page, there's a link to a thing called Pro Snippets. And what snippets are they are small pieces of code that show you how to accomplish a specific task. So in many cases, you can just take these as is and copy and paste them into your own apps. And you can see from the very small text on the right-hand side that we've got quite a few on the geodatabase side. There is, of course, a full API reference that you can get to from the SDK homepage, listing out all the classes and methods, and that's all. So thank you very much for listening today and watching today. If you want the session materials, they are available by scanning this QR code. Thanks and have a great day.